On January 13th, NASA's Europa Clipper spacecraft was reportedly passing through the massive iron tail of 3I Atlas. This event opens up the possibility that the spacecraft's sensors may have collected data on interstellar material from an extremely large distance. It is considered a rare form of indirect contact in the history of space exploration, in which a mission not designed for this purpose is still able to record traces of an object originating from outside the solar system. In parallel with this event, 3I Atlas has exhibited unusual geometric characteristics, including a powerful jet of gas consistently pointing toward the Sun, a rotation axis nearly aligned with the Sun, and an orbit lying close to the ecliptic plane. This combination of factors has a very low probability of occurring if a purely random origin is assumed, placing significant strain on many existing astronomical models. At the same time, unusual silence from United States government agencies, particularly the CIA's refusal to confirm the existence of records related to 3I Atlas, combined with the loss of signal from the MAVEN spacecraft during its close approach to the object, has further increased the level of suspicion. When scientific anomalies and institutional responses converge, 3I Atlas is increasingly viewed as a potential black swan, raising profound questions about the current limits of human understanding of the universe and what may be hidden beyond ordinary observation. Next, we will explore the latest discoveries as NASA approaches 3I Atlas at the closest distance ever recorded. When Europa Clipper passed through the ion tail of 3I Atlas, the spacecraft was reported to register subtle vibrations, along with brief system alerts arising not from impact with solid material, but from rapid changes in the surrounding plasma environment. These fluctuations temporarily interfered with onboard sensors, prompting the spacecraft to initiate automatic self-recalibration sequences rather than entering an emergency mode. At the same time, scientific instruments detected unusual optical and electromagnetic signals, indicating that 3I Atlas is releasing material with properties unlike those of ordinary comets. The data recorded a faint luminescence with bluish or greenish tones, consistent with ionized gas along with traces of heavy elements and organized plasma flows. Rather than a violent collision, the event resembled a spacecraft traveling through a highly energized region of space, revealing that 3I Atlas is not an inert mass, but an active celestial object continuously releasing matter and energy into its surrounding environment. Measurements showed 3 Atlas moving at approximately 46.9 kilometers per second relative to the Sun, a value that immediately separated 3 Atlas from the familiar population of comets and asteroids bound to solar gravity. This speed was not a brief spike near perihelion, but a sustained condition indicating that 3I at last entered the solar system already carrying immense kinetic energy from beyond. In classical celestial mechanics, such velocity is not impossible, yet it demands an origin story that stretches across interstellar distances and long timescales. 3 at last could have been ejected from its home system by gravitational chaos, perhaps slingshot outward during planetary migration or stellar interaction, and then wandered through the galaxy until chance aligned paths with our Sun. As observation shifted from orbital mechanics to physical structure, the appearance of an extended ion tail around 3 Atlas marked a clear transition from motion to material behavior. Ion tails are common features of comets, yet the ion tail associated with 3 Atlas immediately stood out because of its sheer scale and coherence qualities that resisted casual explanation. Measurements suggested that the ion tail of 3 Atlas extended for tens of millions of kilometers, reaching lengths that rivaled or exceeded the distance between planets. In conventional cometary physics, an ion tail forms when solar ultraviolet radiation ionizes gases released from the nucleus, after which the solar wind stretches those charged particles away from the Sun. This process is well understood and usually produces structures that are diffuse dynamic and highly responsive to changes in solar activity. With 3 at last, however, the ion tail appeared unusually long, sharply defined and persistent across observation windows that spanned weeks rather than hours. Data collected from multiple observatories indicated that the ion tail of 3I Atlas maintained its structure even as the object moved rapidly through varying plasma environments. Such stability is not forbidden by physics, yet it typically requires either exceptionally high production rates of ionized material or a geometry that favors continuous replenishment. When researchers estimated the required mass loss to sustain an ion tail of this scale, The implied output from 3 Atlas approached the upper bounds of what is normally expected from a body of its estimated size. This discrepancy introduced an anomaly that was subtle but persistent. If 3 Atlas were releasing material naturally, then either the nucleus was unusually rich in volatile compounds, or the interaction with the solar wind was operating under conditions not commonly observed. Neither explanation could be ruled out, yet both carried implications that extended beyond a simple classification as an ordinary interstellar comet. Emotionally, the image of the ion tail altered how 3I Atlas was perceived. The vast luminous structure trailing behind 3I Atlas transformed the object from a distant point of light into a presence that occupied space on an interplanetary scale. For observers, the ion tail of 3 Atlas acted as a visual bridge between abstract data and intuitive impact, quietly reinforcing the sense that this visitor was interacting with the solar system in a way that felt amplified rather than incidental. As attention lingered on the unusual size of the ion tail, the narrative surrounding 3 Atlas naturally drifted toward questions of proximity and consequence. If the ion tail of 3 Atlas extended so far, then space around the object was no longer empty, and the possibility of interaction with passing spacecraft became more than theoretical, guiding the inquiry toward the next layer of observation. As trajectory simulations were refined with higher temporal resolution, attention turned toward the spatial relationship between Atlas and one of humanity's most complex deep space missions, Europa Clipper. Europa Clipper was never intended to encounter an interstellar object, yet the expanding ion environment of Atlas introduced an unexpected overlap between natural motion and engineered presence. Calculations indicated that while Europa Clipper would remain physically distant from Atlas itself, the separation between Europa Clipper and the extended ion tail of Atlas narrowed to scales that could not be ignored. Estimates placed the closest approach at roughly 150 million kilometers a distance that sounds vast in human terms, yet becomes comparatively intimate when measured against the known lengths of large ion tails. If the ion tail of Atlas extended as observation suggested, then Europa Clipper may have passed through a region permeated by charged particles originating from Atlas. This possibility did not imply collision or danger, yet it reframed the encounter as an environmental interaction rather than a simple flyby. In standard mission planning, spacecraft are designed to tolerate fluctuating plasma conditions, especially near planets like Jupiter, where magnetic fields dominate the local space weather. What made this situation unusual was not the presence of plasma, but its potential source, because Atlas introduced material that was neither planetary nor solar in origin. For the first time, Europa Clipper's instruments may have sampled a medium shaped by an interstellar object, rather than by the Sun or a planet. The ultraviolet spectrographs and plasma sensors aboard Europa Clipper were capable of detecting subtle changes in particle composition and energy distribution. If Europa Clipper recorded anomalies during this interval, those signatures would not immediately reveal their origin, yet they would quietly expand the dataset associated with Atlas. Atlas, therefore, became not just an object of observation, but a contributor to an unplanned experiment in interstellar material science. Emotionally, this narrowing distance carried a gentle tension rather than alarm. The idea that a spacecraft designed to study an icy moon might drift through the extended influence of Atlas blurred the boundary between exploration and encounter. As Europa Clipper continued on its trajectory, the proximity to Atlas served as a reminder that space is not empty, and that even distant paths can intersect in ways that subtly reshape how observation unfolds. As ultraviolet data streams were reviewed, the question surrounding Atlas shifted from distance to composition, because light in this range carries chemical fingerprints rather than images alone. Ultraviolet instruments are sensitive to ionized gases and specific atomic transitions, and the spectra associated with Atlas therefore offered a rare opportunity to look beyond brightness into substance. Initial UV readings were consistent with what one might expect from ionized cometary material, yet the signal associated with Atlas appeared stronger and more structured than typical dust-dominated emissions. This distinction mattered because dust reflects and scatters light broadly, while chemical species absorb and emit at precise wavelengths that can be traced back to specific elements or molecules. When analysts compared the UV profiles linked to Atlas against known comet databases, subtle mismatches emerged that resisted immediate categorization. Some features aligned with common volatiles, yet others suggested ion populations that would normally dissipate quickly under solar radiation unless continuously replenished. This anomaly opened a narrow interpretive gap where the data from at last could represent either an unusually rich dust environment or the presence of less familiar chemical processes. If dust dominated the signal, then at last would still fit within the outer edges of known comet behaviour, albeit at an extreme scale. If chemical traces were responsible, then at last would be introducing material whose origin and stability demanded closer scrutiny. The ambiguity itself carried emotional weight because Atlas was not offering a clear answer, only a choice between interpretations that pointed in different directions. For scientists, this uncertainty was not failure but invitation, a reminder that Atlas was being sampled indirectly through light rather than directly through contact. As ultraviolet analysis continued, the data from Atlas became a bridge between structure and implication, easing the narrative toward deeper questions without forcing premature conclusions. Within the established framework of cometary physics, an anti-tail is not entirely unknown, yet it occupies a narrow and often misunderstood corner of observational astronomy. An anti-tail appears to point toward the Sun rather than away from it, and this apparent reversal has historically been explained as a projection effect, caused by viewing geometry rather than by true physical motion. When sunlight illuminates larger dust grains released earlier in a comet's path, those particles can align along the orbital plane, creating the illusion of a tail that defies solar pressure. In most documented cases, an anti-tail is faint, transient, and highly sensitive to changes in viewing angle. The structure usually collapses or fades as the geometry shifts, reaffirming that the phenomenon is optical rather than dynamic. For decades, this explanation has been sufficient, and it has allowed astronomers to categorize anti-tails as curiosities rather than challenges to theory. The situation becomes more complex when these expectations are applied to Atlas, because the sunward feature associated with Atlas does not behave like a typical projection artifact. Observations of Atlas indicate a structure that is narrow, coherent, and persistent across multiple observation windows, even as the viewing geometry evolves. This persistence introduces a subtle tension because projection-based anti-tails should lose definition rather than maintain it. In classical models, solar radiation pressure and the solar wind dominate the behavior of charged particles, forcing material away from the Sun with predictable efficiency. A stable sunward-oriented structure therefore requires either unusually large particles that resist these forces, or a continuous process that replaces material as quickly as it is removed. When applied to Atlas, both explanations stretch toward the edge of what is normally observed without clearly crossing into impossibility. Atlas remains bound by physics, yet the anti-tail associated with Atlas occupies a grey zone where familiar mechanisms feel incomplete rather than incorrect. This ambiguity does not overturn cometary theory, but it places Atlas at a boundary where explanations become conditional rather than definitive. Emotionally, the presence of a persistent anti-tail alters perception more than understanding. The image of Atlas presenting material toward the Sun carries an instinctive contradiction that lingers even after rational explanations are reviewed. As the discussion of anti-tails transitions from optical illusion to structural persistence, Atlas quietly shifts the narrative from known exceptions toward unresolved questions, preparing the ground for deeper examination without forcing belief or rejection. When the Hubble Space Telescope turned its attention toward Atlas, the discussion surrounding the sunward structure moved from theoretical debate into the domain of direct measurement. High-resolution imaging revealed that the feature associated with Atlas was not a diffuse glow or a loosely aligned sheet of particles, but a sharply defined structure extending outward with remarkable coherence. The length of this structure was estimated at approximately 400,000 kilometers a scale that immediately reframed the conversation about what was being observed. At that distance, the structure linked to Atlas spanned nearly the space between Earth and the Moon, and it did so while maintaining a narrow profile rather than dispersing into a cloud. This geometry alone distinguished Atlas from previously documented cases of projection-based anti-tails, which tend to widen and fade with distance. The Hubble data showed that the feature associated with Atlas retained its shape across multiple exposures, even as the object continued its rapid motion through the inner solar system. Temporal analysis added another layer of complexity, because the structure associated with Atlas persisted over days rather than hours. If the feature were purely optical, small changes in viewing angle should have degraded its alignment, yet the images suggested continuity rather than collapse. Atlas therefore presented observers with a structure that behaved less like a fleeting illusion and more like a sustained outflow. Spectral hints embedded in the Hubble observations suggested that the material forming this structure was ionized, meaning it should have been strongly influenced by solar wind forces. Under ordinary conditions, such material would be swept away from the Sun almost immediately, yet the structure linked to Atlas remained oriented in defiance of that expectation. This did not require new physics, but it demanded conditions that were rarely, if ever, observed at this scale. For scientists, the Hubble images of Atlas became a pivot point between comfort and unease. The data were clear, the measurements were consistent, and the instruments were trusted, yet the implications resisted tidy categorization. Atlas was not breaking known laws, but it was occupying a region of parameter space, where known laws produced strained explanations rather than satisfying ones. Emotionally, the sheer size of the structure altered how Atlas was imagined. Atlas was no longer just a fast-moving nucleus with a tail, but a system interacting with solar forces across hundreds of thousands of kilometers. As the Hubble observations settled into the growing archive of data, Atlas carried the narrative forward from optical curiosity into structural reality, easing the inquiry toward questions of mechanism without demanding immediate resolution. In standard cometary behavior, solar radiation pressure acts as a constant reliable force that pushes dust and ionized material away from the Sun with predictable efficiency. This pressure increases as objects move inward, and for most comets it explains both the direction and the spread of their tails without requiring additional assumptions. When this framework is applied to Atlas, however, a discrepancy emerges that is subtle but persistent. For a structure to remain oriented toward the Sun, radiation pressure would need to be either dramatically weaker than expected or continuously countered by another process. Neither condition is easily satisfied in the environment where Atlas was observed, because solar output during this period remained within normal ranges. Measurements of solar wind density and velocity showed no anomalies, large enough to reverse or neutralize the expected outward force. Additionally, radiation pressure acts more strongly on smaller, brighter particles, which should be stripped away first, leaving behind a faint and diffuse remnant. The sunward structure associated with Atlas did not display this behavior, instead remaining narrow and luminous over extended distances. This mismatch does not violate physics, yet it suggests that radiation pressure alone cannot account for what Atlas was presenting. As a result, the discussion naturally shifted from whether radiation pressure failed to how Atlas might be maintaining balance within an environment that should favor dispersion. As attention moved from structure to orientation, the rotational behavior of Atlas introduced a new layer of quiet complexity into the unfolding picture. By tracking subtle variations in brightness and the slight wobble of features associated with Atlas, astronomers were able to infer the orientation of the spin axis relative to the Sun. The results suggested that the rotational axis of Atlas was aligned unusually close to the solar direction, a configuration that immediately stood out against expectations for a free-tumbling interstellar body. In most natural scenarios, objects like Atlas arrive with random spin states shaped by ancient collisions and long exposure to gravitational chaos. These spin axes tend to point in arbitrary directions, and any alignment with the Sun is typically brief and accidental. With Atlas, however, the inferred orientation appeared stable over time, implying that the sunward alignment was not a fleeting coincidence, but a persistent condition. This alignment carried practical consequences for how Atlas interacted with solar energy. If one rotational pole of Atlas remained consistently exposed to sunlight, then heating would be concentrated rather than distributed evenly across the surface. Such a configuration could in theory support sustained outgassing or localized activity, yet it would also require the rotation of Atlas to be finely balanced rather than chaotic. Models that incorporated normal rotational dynamics struggled to reproduce this behavior without invoking highly specific initial conditions. Atlas could still be natural, yet the range of natural histories capable of producing such alignment narrowed significantly. The more precisely the axis of Atlas appeared to track the Sun, the more the discussion shifted from randomness toward constraint. Emotionally, this realization altered the tone of inquiry surrounding Atlas. The image of Atlas maintaining a steady orientation as it crossed the inner solar system felt less like debris drifting through space and more like a body interacting deliberately with its environment. This perception did not assert intention, yet it softened the boundary between passive motion and active configuration. As the data continued to support a sunward-oriented spin axis, Atlas carried observers into a deeper question about probability and geometry. The alignment itself was not impossible, but its persistence invited statistical reflection, easing the narrative toward an examination of how often such order emerges from chance alone. Beyond the orientation of the spin axis, the broader geometry of Atlas revealed another layer of improbability that emerged only when motion was placed within a statistical frame. The trajectory of Atlas was not steeply inclined relative to the solar system, but instead lay close to the ecliptic plane, the same flattened disk in which Earth and the major planets orbit. For objects born within the solar system, this alignment is common, yet for interstellar visitors like Atlas, it is distinctly uncommon. Most interstellar objects are expected to arrive from random directions, cutting through the planetary plane at sharp angles, before vanishing back into interstellar space. Simulations of such arrivals produce a wide distribution of inclinations, with only a small fraction skimming the ecliptic by chance. When the orbit of Atlas was placed within these models, the result fell far into the tail of the distribution, rather than near its centre. Researchers quantified this deviation, using probabilistic estimates rather than intuition. When the near ecliptic orbit of Atlas was combined with the sunward aligned spin axis, the joint probability dropped to approximately 1 in 10,000 under assumptions of random orientation. This figure did not represent impossibility, yet it marked a threshold where coincidence begins to feel statistically strained. Probability alone does not assign meaning, and science resists narratives built purely on rare outcomes. Yet probability does shape expectation, and Atlas repeatedly occupied regions where expectation thinned. The geometry of Atlas therefore became not just a curiosity, but a cumulative pressure point where multiple low-likelihood features converged. In practical terms, this alignment increased the duration and quality of observational coverage. Atlas remained within the same observational corridor as Earth-based telescopes and space assets for longer than a steeply inclined object would allow. This prolonged visibility fed back into the narrative because it enabled deeper scrutiny, while simultaneously benefiting from the very geometry under question. Emotionally, the convergence of alignment and probability introduced a subtle shift in tone. The numbers surrounding Atlas did not demand alarm, yet they discouraged indifference. Each additional constraint made the story of Atlas feel less like noise and more like signal. As observers absorbed the implication of a 1 in 10,000 configuration, Atlas transitioned from an object that merely passed through space into one that seemed finely placed within it. This realization did not resolve the mystery of Atlas, but it gently narrowed the field of explanations, preparing the inquiry to move from geometry toward consequence, where alignment begins to matter, not just statistically, but dynamically. As the trajectory of Atlas carried it outward from the inner solar system, attention naturally shifted toward the region dominated by the largest gravitational influence short of the Sun itself. Jupiter occupies this role not merely as a massive planet, but as the anchor of a vast gravitational domain known as the Hill radius, within which Jupiter's influence competes with and temporarily overcomes solar gravity. The Hill radius of Jupiter extends tens of millions of kilometers into space, forming a diffuse boundary where passing objects can experience subtle but meaningful perturbations. When orbital models placed at last on a course that would graze this boundary, the encounter was not classified as close in planetary terms, yet it was close enough to matter dynamically. Atlas would not plunge into Jupiter's atmosphere, nor would Atlas be captured outright under ordinary conditions, but the geometry of the approach positioned Atlas within a zone where interaction becomes possible, rather than hypothetical. This distinction is important, because the Hill radius represents a transition region, rather than a hard edge, and objects passing through it can exchange energy in complex ways. In classical celestial mechanics, most fast-moving bodies pass through a planetary Hill sphere without consequence, entering and exiting too quickly for gravity to do more than bend their paths slightly. Atlas, however, approached Jupiter with a combination of high velocity and precise alignment that maximized the duration of exposure to Jupiter's gravitational gradient. This did not guarantee interaction, yet it created an opportunity window that was unusually well defined. For observers, the approach of Atlas toward Jupiter introduced a new emotional cadence into the narrative. Up to this point, Atlas had been defined by observation and inference, but Jupiter represented a stage where effects could become measurable rather than abstract. Any interaction within the Hill radius of Jupiter, even a subtle one, would leave fingerprints in trajectory timing or surrounding plasma environments. The possibility of interaction did not require extraordinary assumptions. Natural tidal effects, weak gravitational focusing, or the shedding of material under stress all fall within known physics, and at last remained firmly inside these boundaries. Yet the presence of such a massive planetary system ahead gave the motion of at last a sense of direction rather than drift. As at last continued toward Jupiter, the hill radius stood not as a promise of disruption, but as a threshold of consequence. Crossing that threshold meant that Atlas would no longer be shaped only by the Sun, but would briefly enter a region where another giant voice joined the gravitational conversation. This shift prepared the narrative for a deeper question, because once interaction becomes possible, the absence or presence of outcome begins to matter just as much as the path itself. As the discussion moved from opportunity to mechanics, the problem of capture brought the story of Atlas into direct contact with hard numerical limits. At the distance where Atlas would pass Jupiter, the escape velocity imposed by Jupiter's gravity was measured at roughly 2.2 kilometers per second. This number defines a strict boundary because any object moving faster than that threshold at that distance cannot remain bound without losing energy. The approach velocity of Atlas relative to Jupiter was calculated at approximately 66 kilometers per second. When these values were compared, the implication became unavoidable, because Atlas was moving more than 60 kilometers per second, too fast to be captured by Jupiter under purely gravitational interaction. This gap between approach speed and escape speed created what physicists describe as a delta V problem, a mismatch that cannot be resolved by passive motion alone. In natural fragmentation events such as when a comet breaks apart due to thermal stress or tidal forces, the separation speeds of fragments are small. Even the most violent natural outbursts impart velocities measured in meters per second, or in extreme cases a few kilometers per second. For Atlas, the required change in velocity to leave behind a fragment within Jupiter's influence would be orders of magnitude larger than anything observed in natural processes. This is where the paradox sharpens without crossing into speculation. If Atlas were to shed material during the encounter with Jupiter, and that material became gravitationally bound, then the energy budget would contradict known mechanisms. Atlas would not simply be bending its path, but would be undergoing an energy redistribution that lacks a passive explanation. Importantly, this does not predict that capture will occur, only that capture would be deeply informative if it did. The absence of a new bound object after the encounter would reinforce natural expectations, while the presence of one would demand re-examination. Atlas therefore transformed the encounter with Jupiter into a conditional experiment written by celestial mechanics rather than by intention. Emotionally, the delta V paradox carried a quiet gravity of its own. Numbers that large do not invite drama, yet they impose clarity, and clarity can feel unsettling when it removes comfortable middle ground. Atlas did not threaten physics, but Atlas positioned itself at a boundary where outcomes become binary rather than ambiguous. As the timeline progressed toward the Jovian encounter, the narrative surrounding Atlas became anchored to this paradox. Either nothing unusual would happen or something would, and both possibilities carried weight. With the delta V problem unresolved by nature alone, Atlas moved forward as a test not of belief, but of consequence, bridging geometric possibility into physical accountability. As spectroscopic analysis deepened the appearance of atomic nickel in the surrounding environment of Atlas, introduced a chemical note that felt unexpectedly heavy. In astrochemistry, nickel is not unknown, yet nickel is rarely observed in isolated atomic form within cometary comas, especially at distances where thermal processes are weak. When Atlas was examined through high-sensitivity instruments, the spectral signatures associated with nickel stood out against the usual dominance of lighter elements. Under natural conditions, nickel is typically locked inside refractory minerals bound tightly within solid grains that require extreme heating to liberate individual atoms. Such heating usually occurs very close to a star where intense radiation can break chemical bonds and release heavy metals into the gas phase. Atlas, however, displayed nickel signatures while remaining far from conditions that would normally enable this process. Researchers considered whether Atlas could simply be unusually rich in metallic inclusions, remnants of a violent formation environment around another star. This explanation remains plausible, yet it requires Atlas to carry a composition that diverges significantly from known cometary analogues. When modelled against standard outgassing scenarios, the nickel abundance associated with Atlas appeared elevated beyond what passive sublimation would easily explain. The presence of nickel altered how the material surrounding Atlas was interpreted. Nickel atoms interact strongly with electromagnetic fields, and their behaviour within plasma environments can differ markedly from that of lighter volatiles. If Atlast were releasing nickel continuously, then the physical processes governing the coma of Atlast would need to account for sustained liberation of heavy elements. Emotionally, nickel carries an associative weight that is difficult to ignore. On Earth, nickel is a cornerstone of high-temperature alloys and engineered systems, not because it is exotic, but because it is durable. This association does not imply technology, yet it colours perception, because Atlast was now linked to an element more commonly discussed in metallurgy than in icy debris. As scientists held these observations at arm's length, the nickel signatures associated with Atlast became a pivot between chemistry and implication. Atlast remained consistent with physics, yet the chemistry of Atlast felt displaced from the familiar narrative of frozen interstellar rubble. This displacement did not demand extraordinary conclusions, but it quietly expanded the space of questions, easing the inquiry from structure into composition, and from composition toward purpose without forcing the leap. As compositional analysis expanded beyond metals, the ratio between carbon dioxide and water in the emission surrounding Atlast introduced another quiet disruption to familiar expectations. In most comets observed within or beyond the solar system, water dominates volatile release, while carbon dioxide appears as a secondary component that rises only under specific thermal conditions. With Atlast, however, measurements indicated a carbon dioxide to water ratio several times higher than what is typically recorded even when distance from the Sun is taken into account. Carbon dioxide and water respond differently to solar heating, because carbon dioxide can sublimate at lower temperatures than water ice. This behaviour allows carbon dioxide-rich bodies to become active farther from the Sun, yet even among such objects, water eventually asserts dominance as proximity increases. Atlast resisted this pattern, maintaining an elevated proportion of carbon dioxide relative to water across multiple observation intervals. Researchers explored whether Atlast could simply originate from an unusually cold environment, where carbon dioxide ice accumulated more efficiently than water ice. Such an origin is possible, yet it would place Atlast among a small and poorly sampled population of bodies whose chemistry reflects extreme formation conditions. When chemical models were adjusted to fit the observed ratio associated with Atlast, they required assumptions that sat at the margins of established cometary diversity. The technical implications of this ratio are subtle but meaningful. Carbon dioxide-driven activity can generate more focused and sustained gas flows than water-dominated sublimation, especially when release is localized rather than global. If Atlast were venting carbon dioxide preferentially, then the dynamics of its surrounding coma and tail would differ from those of a water-rich comet, altering how Atlast interacts with solar radiation and plasma. Emotionally, the chemistry of Atlast began to feel less accidental and more selective. Water is the most common volatile in icy bodies, while carbon dioxide dominance suggests either unusual inheritance or unusual processing. This does not imply engineering, yet it introduces a sense that Atlast is expressing a chemical personality rather than statistical average. As carbon dioxide and water measurements continued to align around this elevated ratio, Atlast quietly reinforced a theme already emerging from motion and structure. Atlast did not violate known chemistry, but Atlast consistently occupied edge cases where natural explanations require careful qualification. This persistence did not close the narrative, yet it nudged interpretation toward a space where chemistry, like geometry, begins to feel constrained rather than random, preparing the inquiry for questions that extend beyond composition alone. As Atlast approached the region of Mars, attention focused on a narrow window of time when one of humanity's most valuable atmospheric probes was positioned to observe the encounter. The MAVEN spacecraft had operated reliably for years in Martian orbit, collecting data on plasma particles, and the interaction between Mars and the solar wind and nothing in its prior performance suggested vulnerability. When orbital timelines were synchronized, Atlast and MAVEN were predicted to share overlapping observational geometry during the closest approach, creating an opportunity that scientists had been anticipating for months. According to mission logs, MAVEN was functioning normally in the hours leading up to the encounter with Atlast, with stable telemetry, nominal power levels, and no indications of subsystem stress. As Atlast entered the region of interest, MAVEN was scheduled to collect high-resolution measurements of charged particles and electromagnetic conditions, precisely the data needed to characterize an interstellar visitor. Then, within a remarkably narrow span of time surrounding the predicted closest approach, communication with MAVEN was lost. Official statements described the event as a technical anomaly potentially associated with space weather, noting that solar activity can occasionally disrupt spacecraft operations. However, contemporaneous solar monitoring data showed no exceptional flare or storm that would clearly account for a complete and unrecoverable loss of signal. This discrepancy did not implicate Atlas directly, yet it created an uncomfortable temporal correlation that could not be ignored. Engineers reviewed redundancy pathways and fail-safe protocols, yet MAVEN did not recover, and the spacecraft transitioned from an active observer to silent hardware in orbit. For at last, this moment became a boundary in the narrative because the closest planned in situ observation coincided precisely with the disappearance of the instrument designed to make it. The timeline alone did not establish causation, yet timelines are often where questions begin rather than end. Emotionally, the loss of MAVEN altered the tone of inquiry surrounding At Last. What had been an exercise in passive observation now carried the weight of absence, because data that should have existed simply did not arrive. As At Last moved on from Mars, the silence left behind by MAVEN lingered not as proof of interference, but as a gap in knowledge that reshaped how subsequent encounters would be interpreted. In the absence of direct data from MAVEN, one hypothesis emerged quietly and remained carefully framed because it touched the boundary between natural phenomena and defensive response. This hypothesis proposed that Atlas could have generated an electromagnetic disturbance strong enough to disrupt sensitive spacecraft electronics, not as an act of aggression, but as a byproduct of interaction. Electromagnetic pulses are not exclusive to technology, because natural plasma instabilities can also produce sharp spikes in electromagnetic energy under specific conditions. In space, physics' rapid changes in charged particle density can induce transient electromagnetic effects, particularly when objects move at high velocity through magnetized environments. Atlas, traveling swiftly and surrounded by an extended ion structure, could in principle create localized conditions where such disturbances arise. This interpretation does not require intention, yet it reframes Atlas as an active participant in its environment rather than a passive body. A more speculative branch of the hypothesis considered whether Atlas might possess a mechanism that incidentally shields its immediate surroundings. In this framing, any electromagnetic disturbance associated with Atlas would function less like a weapon and more like a boundary, similar to how strong magnetic fields naturally exclude charged particles. Atlas would not need to target MAVEN specifically, because proximity alone would determine exposure. Engineers are cautious with such ideas because spacecraft failures often appear mysterious until mundane causes are fully explored. Atlas therefore remains separated from attribution, and the EMP hypothesis is treated as a conditional explanation rather than a conclusion. Still, the alignment of timing between Atlas's closest approach and the loss of MAVEN encourages continued discussion rather than dismissal. Emotionally, the concept of a defensive reaction carries a different weight than that of random malfunction. Atlas becomes less like scenery and more like a presence, not because it intends harm, but because its interactions may have consequences beyond observation. This shift in perception does not assert hostility, yet it alters the narrative tone from neutral curiosity toward cautious awareness. As the hypothesis circulated, it remained bounded by uncertainty, because no direct measurement confirmed such an event. Atlas did not announce its influence, and MAVEN did not return to explain its silence. What remained was a possibility shaped by timing physics and absence, allowing Atlas to occupy a space where reaction and environment blur, and where the line between observation and interaction becomes increasingly difficult to define. As the scientific discussion unfolded in public view, a parallel response emerged within institutional channels, defined less by data than by deliberate silence. When requests for information related to Atlas reached intelligence agencies, the reply was not confirmation or denial, but a carefully constructed refusal known as the Glomar response. This form of reply states that an agency can neither confirm nor deny the existence of records, and it is used sparingly reserved for situations where acknowledgement alone is considered sensitive. The historical origin of the Glomar response dates back to the Cold War, when it was first deployed to conceal the existence of a covert operation involving the recovery of a sunken submarine. In that context, the response was not about hiding information already known, but about preventing adversaries from learning what the government was capable of knowing. Over time, this mechanism became a legal tool to protect sources, methods, and strategic awareness rather than specific facts. What makes its application in the case of Atlas notable is the category of subject it addresses. Celestial objects are typically discussed openly because they are observable by anyone with the appropriate instruments, and secrecy offers little practical advantage. Invoking a Glomar response in relation to Atlas therefore suggested that the sensitivity lay not in the object itself, but in the way it was being monitored or interpreted. Historically, the Glomar response has been associated with nuclear capabilities surveillance platforms and advanced detection systems. Its appearance alongside Atlas subtly repositioned the object within a framework usually reserved for strategic technologies, rather than natural phenomena. This shift did not reveal hidden knowledge, yet it signalled that the flow of information surrounding Atlas had entered a different administrative domain. Emotionally institutional silence often speaks louder than disclosure. The refusal to acknowledge records does not assert danger, but it alters perception, because it implies that awareness itself carries weight. Atlas remained visible in the sky unchanged by policy, yet the historical precedent of the Glomar response placed a quiet barrier between observation and explanation. As this barrier settled into the narrative, Atlas became entangled not only with physics and chemistry, but with the history of secrecy. This entanglement did not answer questions, yet it reframed them, preparing the ground for a final consideration of why silence might accompany an object that by all appearances simply passed through space. The question of why the Glomar response would be applied to Atlas arises not from speculation, but from the mismatch between policy and precedent. Atlas is visible to civilian telescopes tracked by public observatories and discussed openly in scientific forums, which makes secrecy about the object itself impractical. This tension suggests that the sensitivity does not reside in the existence of Atlas, but in the methods used to observe, interpret, or contextualize Atlas within broader monitoring systems. Modern surveillance extends far beyond optical telescopes because governments maintain networks capable of detecting electromagnetic emissions, anomalous trajectories, and subtle energetic disturbances. If Atlas triggered attention within such systems, acknowledging the existence of related records could reveal capabilities that agencies prefer to keep opaque. In this framing, Atlas becomes less a classified object and more a classified test case for detection infrastructure. Another possibility centers on uncertainty rather than certainty. If early analyses of Atlas produced ambiguous or internally conflicting interpretations, institutional caution would favor silence over premature disclosure. The Glomar response allows agencies to pause to assess and to avoid anchoring public narrative to conclusions that may later change. There is also a psychological dimension to secrecy. Public acknowledgement that Atlas is being treated as exceptional could amplify speculation and erode trust if later revisions undermine early statements. By declining to confirm, interest agencies preserve flexibility, while shifting attention back toward open scientific discourse.